Hi, and welcome to today's webinar, the fourth in our series of webinars on PFAS remediation. Today's webinar is Global Success Stories from the Field. I'm Connor Walsh, the Chief Executive Officer of OPEC Systems. I'm joined today with Dave Burns, our lead scientist. And then all the way from Sweden, we've got Peter Murphy, the Managing Director of OPEC Systems, and Helena Henriksson, who is both the founder and the head of research and development for NBTech Solutions in Sweden. Welcome, guys. We want this to be a really interactive webinar. So down in the bottom right-hand corner of your screen, you'll see a chat box. Please click on that during the webinar if you've got questions, and we'll come back to those questions at the end when we do a question and answer session. Based on the webinars we've had so far, we expect this webinar to go for just a little bit over 60 minutes and then the question and answer session at the end of that time. If you haven't seen the first three webinars we've done, they're available on the OPEC Systems website. Really encourage you to go and have a look at those webinars. They give a really nice snapshot of OPEC's journey in developing the SAFF PFAS remediation solution we now offer over the last 3 or 4 years. Just a rough agenda. We're going to carry on from webinar 3, give you a quick update on what surface active foam fractionation is and how it works. We'll look at the water treatment plant we've got at Oki, some of the results from there, and how we've taken that quite big plant down into the containerized SAFF 40 and SAFF 20 units we're offering now. We'll take you to Sweden to have a look at the SAFF 40 that we commissioned earlier this year. We're going to chat to Helena about why she chose that SAFF 40 solution. We'll also look at the bench scale testing that Helena and her team have been doing using SAFF across a range of different water chemistries and look at those results. We'll give you an update of the work and research we're currently undertaking. And finally, we'll outline OPEC's plans to meet future demand for the SAFF 20 and SAFF 40 units. And then if we've got questions, we'll go straight into the question and answer session. So Pete, I'll probably start with you. We've gone from a big SAFF water treatment plant at Oki down to a really compact plug and play system in Sweden. For those people who are new to surface active foam fractionation, can you just give us a little bit of an overview of what SAFF is and how it works?
Yeah, sure, mate. So, I mean, we've covered this a little bit in previous webinars, so I won't labour the point too much, but I guess it continues to excite us in terms of what foam fractionation really is. So, at its most basic form, fractionation is really relying on the natural chemistry of fluorocarbon compounds to adhere or to bond to the surface of an air bubble. So if you look on the schematic we've got up there, you've got this fluorinated tail, which is hydrophobic, and it likes to be on or in the air bubble, whereas you've got these functional heads, sulfonated carboxylate heads that are hydrophilic and like to be outside. So you've got this kind of chemical match made in heaven on the surface of an air bubble. And so as we rise air bubbles through columns of PFAS contaminated water, large tanks basically, then those PFAS compounds agglomerate on the surface of the air bubble, they rise with the air bubble, and then they accumulate on the surface and present as a foam. And so our art and our engineering design is all around harvesting that foam. We do that a couple of different ways. We do that in a passive sense using a kind of spillover weir design, very similar to kind of traditional protein skimmers in aquariums. And then as we move from that kind of separation stage into the concentration stages further in our plant, which we'll discuss a bit later, then we use this a vacuum-based approach. And so the principle is actually pretty easy. I mean, there's a bit of fancy engineering in there and there's a bit of clever design, but the reality is we put air in, we don't use any chemicals, we don't use any absorbent media like GAC, we don't use any resins, we don't use any membranes, we just use air bubbles in water columns to extract PFAS out of solution, and in its simplest form, that's what it is.
Excellent. Thanks, Pete. Well, I'm going to switch to Dave. So, Dave, a SAFF water treatment plant has been operational in the Army base at Oakey for almost 2 years now. Can you tell us a bit about the results?
Yeah, sure. Well, first of all, it's great to be on the couch again with you.
Yeah, taking Pete's prime spot.
Whilst Pete's in Sweden supporting MVTech with Helena, I've moved one position up on the couch. I'm really happy with the performance of the Oakey plant. It's performed beyond expectations. It's never missed a criteria or a contractual obligation. It's basically pumped 14 million gallons of groundwater through the primary fractionators. Of that, it's concentrated the primary foamate down into 1,800 gallons of secondary concentrate. And of that, we've further reduced that volume down to 6 gallons of tertiary concentrate, which we call super concentrate. And it's a super concentrate that we make available for destruction by others using the various technologies to destroy. And we're kind of agnostic to which destruction technology we use. It's kind of interesting that of the 50% or 50% of that 6 gallons, we've given half of that away through a deed of arrangement with the Department of Defence to those destruction cell developers to test their systems. And it's been in such demand that we've actually had a waiting list for about 12 months. And the other 50% is about to go out to more international destruction cell developers.
There's nothing better than a waiting list as far as I'm concerned.
We should have sold it and made some money out of it.
I did some Googling and I got my numbers wrong earlier today, but that volume of water we've treated equates to about 20 Olympic swimming pools, which is a huge amount of water. How do we achieve those enormous concentration enrichment factors from taking that enormous amount of water down to, as you say, 22 litres,
6 gallons.
6 gallons.
Yeah. It's a question we're often asked. A lot of people, they actually don't believe it in the first instance until we take them through the science. But basically, the way that we are able to do this is by having or designing the process as a multi-stage foam fractionation process where the primary fractionation process strips the PFAS out of the groundwater or the feed water to below the adopted site criteria, as you can see up on the
I think we've got a different slide.
That one's for Oakey. So that one just shows the stripping effect. And then we take the primary foamate, the concentrate from the primary stage, and we pass that through a dewatering or an enrichment process. And it's that enrichment process that uses our patented vacuum technology to make those huge concentration steps or enrichment factors. And it's a combination of both the multi-stage foam fractionation process plus the application of vacuum together is how we actually get those big concentration steps to reduce the final waste into a tiny volume. And that slide there on the screen basically depicts the flow diagram process.
And yeah, that's important because that is the patents around not only the equipment that we're using to vacuum, but also that process, that multi-stage process. So, thanks for that, Dave. Hey, Pete, we're going to go back to you. We started our SAFF journey in a little workshop down in Melbourne here in Australia, and we've now gone international. So talk us through that process.
No worries. Let me just steer in a bit here.
There you go.
So, I mean, we started on this journey probably 6 years ago, I guess. We were sitting on a bench down in Canberra, and the problem with PFAS first came up, and so we didn't even know what it was, to be perfectly frank, at the time. Like, I had some rough idea as an old scientist what we were dealing with, but in terms of how we were going to remediate it, it was a real puzzle to us. So we deal with a lot of complex contaminants in our role as a contractor, but this was one we hadn't looked at. But we went on it's been a long journey, and by about 2018, we'd evolved the science of fractionation far enough to win a contract with the Australian Department of Defence to put a 250,000 litre or a 65,000 gallon a day system into a site called Oakey, which is an aviation base run by the Department of Defence up in Queensland. So that site's been running now for a bit over 2 years. We commissioned it, I think, in May of 2019, so we're coming up to 2 years now since commissioning, about 2.5 since installation, and that system's going well. But along that journey, probably a year or two ago, we realised that we really had to. We had a major problem here, not just in Australia, but all over the world. I think we realised that we had a fairly unique solution in foam fractionation, and part of our challenge was really to communicate that solution to the rest of the world. For quite a while, fractionation hasn't been part of the conversation. Traditional systems like GAC and resin have really taken a lot of the bandwidth, and you know, rightly so. They're established and mature technologies that do a good job. So we've fought hard, I guess, over the last few years to bring foam fractionation into the limelight as a valid and in fact beneficial technique in that PFAS remediation space. And to do that, we've done a lot of re-engineering of the design we had at Oakey. So at Oakey, we had a 100-foot by 80-foot pad to work on. So we had tanks and space everywhere. It was all very relaxed. But we gave the guys the mandate. We want what we've done at Oakey in a 40-foot container. And of course, you know, started off saying that was impossible, but soon enough we re-engineered and managed not just to equal what we were doing at Oakey at that 65,000 gallon a day mark, but we'd actually tripled or quadrupled it. We're looking at 250,000 gallons a day with that system at maximum load. So all in a 40-foot container footprint, ready to plug and play. They're self-bunded, they're automated, they're ready to ship anywhere in the world and start treating PFAS impacted waters. You literally have an influent line that you plug in, a 3-inch cam lock. You have a 3-inch return line for overflow in case there's excess supply, and then you've got an effluent line discharging treated water. You plug a 63 amp power line into it, and away she goes. And that was exemplified at the Telge site here in Sweden, where basically the day we landed, we plugged that system in and we were starting to treat water. So so we set that up for that international market, and now we've got a system here in Sweden. Another one leaves this week for Sweden. The next one goes out to the US, should arrive there in July, August of this year. And then behind that, right through the back half of the year, we've got a number of other systems going to various corners of the globe. So it's a pretty exciting time for us in this foam fractionation space.
It's certainly exciting, and certainly I love the way you challenge the boys to live up to our OPEC's motto of creating intelligent environmental engineering solutions. You put the boys to that challenge. Helena, I'm going to come across to you now if I can. Thank you for joining us on today's webinar. So Helena is both the founder and the head of research and development at Envitech Solutions in Sweden. Envitech's an environmental remediation agency focusing on soil and water remediation with a special interest in PFAS contamination. And Helena, you have been a pioneer, early adopter of our SAFF technology, and is our agent with distribution rights throughout Scandinavia. Perhaps we can start by just asking, how did you come across OPEC and our SAFF technology?
Well, thank you. Well, it was as I was going. I was actually getting an invite to a remediation conference in Adelaide about 1.5 years ago to present the project where we have stabilised PFAS soil over here in Sweden. And prior to my trip, I was browsing LinkedIn just to see what was going on. And I saw David Burns had posted a bit of a teaser post regarding a new method for PFAS water treatment. And as we were running then, as we are now, quite a few PFAS projects here in Sweden, I was very aware of the limitations that, you know, carbon and IX mass poses on those projects. So a new method without filter medias, that I think that was David's hinting on those posts, was something that I was really keen on to look into. So I just sent him a message really and asked him about it. But as there was more information to come, he said, he was kind of secretive. and he wanted me to wait for that, but I'm not good at waiting. So I scheduled a date with him at the conference and picked his brain about the method and the results that you guys had been getting. And it was just so simple and beautiful, and I could immediately just see how I could make it work back home with the challenges that I had here. So I just thought, I'm going to get this to Sweden, and this is what we're going to do. Excellent.
Nice. And understanding some of those challenges, landfill sites can be subject to PFAS plumes and leachate, which have traditionally challenged some of those other remediators you mentioned. Can you talk us through the Talia recycling facility?
Yeah, the Talia landfill was a project that came out quite in the beginning. And as you can see here in this picture, it is as green as the environmental course that we're running here. It is a sealed landfill where water is leaching through the landfill and is collected in the leachate pond. As in most leachate landfills, the leachate therefore contains anything in like everything. So it's like the Long Island iced tea drink of waters. And so apart from, suspended particles that flow into the water, cross contaminants, which are both organic and inorganic, we have high DOC levels and high conductivity, as well as PFAS and PFOA and other PFAS levels. We have about 2,500 nanograms per litre coming in the summer 11. And you can see here in this table just the average concentrations of anything going in. And that's kind of normal for a landfill, I think. What is not normal, or maybe at some landfills, but at this one particularly, we have another challenge, which is called an algae. And there have been several treatment methods trialed at this site, but everyone has failed, and I think it's due to the algae. It's a lot of it, and it's been sampled for just to see what it was. It was sent off to France to be analysed, but they just found that this was a new kind of algae and didn't have a name. But they described it, as you can see here from the lab, as a gelatinous yellow-green conglomerate containing a large number of fine particles. Well, we can't have it not having a name, so I named it, and I named it the Ghost, because you can definitely see it, you cannot touch it, it's there, but you cannot remove it either. So it's really a tough cookie to handle, if I may say so. And this is something that we actually got to trial ourselves, because as we won this project, the SAFF was going to come in and do this for us. We was really excited. But due to COVID, which has just affected every one of us, I think, in different ways, and especially delivery times, we were starting the contract at the 1st of September, but the SAFF plans was about 2 months late. So we decided on, well, since we have 2 months that we need to start on the contract, and like, okay, everyone else people have been trying GAC and other solutions, but at MVTech, we're really good at pre-treatment system. It's one of our core businesses. So we wanted to try it ourselves to really see, like, what if you put in a really good pre-treatment system and gave it all we had? Could we make the carbon work, or how was that going to go? So we did that. We started with sending the water to a flocculant expert, and he picked out a flocculant that he thought would be perfect for this algae. It looked like it anyway in the tests. We also brought in a stripping agent. This we mixed with the water in a 2-stage mixer tank, as you can see here in the picture. From that, after good mixing, we took it to a lamella, just for increasing settling time, into a 38 cubic meter sedimentation tank, and to just get rid of all the particles that we could and everything else. We then had 2 carbon filters, 2 times 1,500 kilos and of activated carbon. Where the first one was just really to knock out anything from DOC to organics and stuff like that. And in the second filter was actually going to handle the PFAS. And I really thought that this was going to work, but as we started it, it just took 4 days, and the PFAS levels going in was just as high as going out. So that was a big waste of money. We had also thought we were going to do a trial with IX resin, and you can see that in the foreground here, the 2 vessels. But as the carbon just failed in 4 days, we didn't see the point. So we never got to that, really.
Well, thanks for that, Helena. That is it's fascinating to just see just how complex that water chemistry is at Talia. And we've got a video now, a short sort of 10-minute video where we're going to look at the commissioning of that SAFF 40 unit at Talia. So we'll go to the video now and then we'll come back to you and Peter at the end of that video.
We're in Sweden at Telga at the Vinning, one of Sweden's largest landfills near the township of Södertälje, just outside of Stockholm. 2 weeks ago, OPEC's SAFF 40 system arrived on site with the task of treating the leachate water that's coming out of the landfill. The leachate, like a lot of leachate waters from landfills, is high in PFAS compounds. In particular, the municipal authorities wanted the landfill to deal with the problem of PFOS and reduce it down to below 50 nanograms per litre or 50 parts per trillion before they could discharge it into the sewer system. So the landfill had tried different systems. They tried a carbon-based system, they tried a resin-based system, all of them blocked up within a matter of days or weeks, and so they decided to invest in the SAFF process to see if it could work to solve their problem. And so I'm here to take you for a bit of a tour and show you what we've done. You can see the leachate water coming out here. It's formed its own nice little iceberg, which is quite cool. The temperature has varied over the last few weeks between 0 and minus 20 degrees Celsius, or for the American audience, somewhere between 32 degrees Fahrenheit and about minus 4 degrees Fahrenheit. So pretty cold and has created some interesting challenges, but I'm excited to show you how we've overcome them and how the system's working. So if you come for a wander, we'll go and have a look. So here we are at the SAFF 40. You can see we've really neatly contained our 40-foot container within a shelter system. The SAFF container itself is fully insulated, it's heated, it's ready to operate in fairly well any location, but we've integrated it in with the shelter so that we've got this kind of consolidated pre-treatment and SAFF system all in one. It's working really well. It's a really neat setup. We've built it on a slab that drains back to the lake, so everything's fully protected in the event that we had some sort of a spill. Running from left to right on your screen, we've got the control system at the far end here, where the operator, through the HMI, is able to control all facets of the system. We've then got a collection tank where the pre-treated water enters. It's about 3,300 litres or about 750 gallons, and then it flows to one of 4 primary vessels. These SAFF vessels are 2,600 litres each, or about 650 gallons. Those systems take about 20 to 25 minutes to process a batch of water, and a little bit like the pistons of a car, one of them's filling, another one's draining while the other 2 are operating. So the outflow from the system is pretty well continuous. If you think of fractionation as 2 separate stages, you've got the separation stage where we're trying to remove the PFAS, and then you've got the enrichment or concentration stage where we're just trying to dewater and minimise our waste stream that contains the PFAS. So the separation phase occurs in the primary separators. By the time we've finished our batch with that contaminated water, we're able to get PFOS, PFOA, PFHXS, a whole bunch of the long chain precursors, a lot of the fluorotelomere alcohols. All of those products are being removed largely down to limits of reporting of between 1 and 10 parts per trillion or nanograms per litre. So it's working really well. That's it. These large primary vessels then discharge their treated water to sewer, and the fractionate, which is what we harvest off the top, it travels to a separate tank down the far end for concentration or enrichment. And this is where we conduct secondary and tertiary fractionation. Through these later stages, we're just dewatering the foam effectively, and we're able to get concentrations in the tens of thousands, even the hundreds of thousands at the moment. Not as good as we're getting with groundwater, but still perfectly adequate for this location. We're treating about 250,000 litres a day, and we're producing somewhere between 10 and 20 litres of hyperconcentrate for disposal and destruction. So it's a pretty good outcome for a place that didn't have a solution to their PFAS problems. Of course, carbons and resins they're very challenging in these waters for those systems to operate because they quickly block and blind up, and there's a high cost of replacing those consumables. With the SAFF system, it just keeps on chugging through. It doesn't mind the cross contaminants, it doesn't mind the high sediment loads, it doesn't mind the high DOC, it doesn't mind the high salinity. It just keeps removing almost exactly as per the predictability model that we developed at Oakey. So we're C6 and above, we're getting virtually 100% removal. So it's going extremely well. We're happy, and I'd have to say I'm almost surprised how well it's working. It took us about 2 days to get it going and processing water, so it really, that plug and play principle that we were trying to adopt really is embodied in the SAFF 40 system. If we come inside, I'll let you see some of the workings. The water from the pre-treatment system enters the tank here via this side hatch. These are pretty conveniently set up. There's just a 3-inch cam lock. So you have an inlet line, and then the second line is a return line or an overflow line. So that just travels back to the source if there's no demand on the water. So the system can sit there with no flow whatsoever for weeks or months on end, and as soon as the flow kicks in, it'll start itself off and away it'll go. We're inside the SAFF container, looking at the initial buffer tank, which would have been on your left-hand side as you were looking at the system. Sorry about the background noise, the system's running. The water that collects in there hits the high level, and then it travels to the next available primary SAFF system. So you can see the hoods are getting a bit gunked up now, but we've got a run of them down into the system here, and it'll select which one of the next 4 is available, and they'll fill up and operate in batch sequence to allow us to treat these 2,600 litre batches as we go. You can see in the silver boxes we've brought all the PLC wiring and control back to central points. We've got our flow meters so that you know how things are working on the way through. You can see we've got a GAC filter there treating the vented air from the system. And once the primary systems discharge via their hoods, that runs along these large grey pipes to the rear of the container, where it ultimately collects in the first primary frac collection tank down this end. As that fills up, a call's made by the secondary and tertiary fractionators, who begin their processes of enriching or dewatering or concentrating that primary frac solution. A lot of the magic lies in these hood systems, which is able to maintain an eye on the vacuum pressure and the blower pressure to try and hold the perfect conditions internally for us to draw off a dry, very enriched foam product, which then travels up to the end again, where it collects in another tank before the tertiary fractionator gets a call. Now this secondary fractionator, sorry about that term, it takes the secondary fractionate and it puts it through a third tertiary fractionation process. We've got another hatch at the far end of the system where the treated water exits again via a 3-inch cam lock, and you can see there it travels down the drain, which ultimately runs to sewer. So contaminated water in one end and clean water out the other. And the hyperconcentrate travels down this line where it collects in an IBC ready for disposal at a later date. This I find the really interesting end of the plant. So we've carved out of the container footprint a 600mm, 2-foot deep vestibule, and housed in it all of the controls and the electronic systems, the PLCs, the HMI, so that we're able to really carefully monitor the system. Our design brief was the best remote telemetry we can offer, and I think we've achieved that. Every single pump in the system, everything that moves basically, has its own control system. So we've got variable speed controllers on all the pumps and motors so that we can adjust those to optimise them. We've got individual switches and power circuits for each of the systems. But I think most importantly, we've got this really functional HMI system that the operator can easily use. You've got a sort of an overview screen just to switch stuff on, just to see how your 4 levels of the primary feed water, the primary SAFF function, the secondary tertiary SAFF function, and the hyperconcentrate functions are performing. And then if you want, you can drill into each of those levels so we can see what's the back pressure on our filters at the moment, how many litres have we got in tanks, what kilowatts is our pump drawing, what step are we up to in the fill process. And we can do that in each of those areas. And so here we are in the primary fractionator area of the SAFF, and each individual SAFF vessel has the ability to be fine-tuned, so we can change the fractionation stages, the time in those stages, the amount of energy we put into those stages, the overall time that stage takes to fractionate. So there's a lot of flexibility of control, and this can be done remotely. You don't have to be here. Effectively, you can do it from your laptop anywhere in the world. And the OPEC Control Centre back in Australia also has constant oversight over these systems, just seeing how they're performing and making sure that we keep them running as well as they can. I think one of the more exciting things for me is we've really gone to a lot of effort just to explore the trends. So we're looking at the different cycles in all of the tanks. How's the rhythm of the system running? Is it all in order? How much air pressure have we got? How are the filters got back pressure? What's the temperature like inside the system? What's the power being drawn? That's a really important one actually, because when you've got a system that doesn't use consumables, requires almost no labour and generates almost no waste, then the single thing that we know will be judged on is how much power does it use. And so we're able to see real time and constantly just how much power the system's drawing. And then there's a whole bunch of other stuff for the client's interest. So we're able to tell them how much water they treated in a given day or in a given week or in a given month. Very handy for invoicing purposes, obviously. We're able to tell them how much power they're using both in the treatment system but also in the ancillary stuff like heaters and mixing pumps in their side of the system. So we're able to give them some fairly good insight into that. We also look at fractionation cycles, how many primaries versus how many secondaries versus how many tertiaries, so we can start to understand our concentration factors and the ratios we're achieving. How effective is it, and is it working well? We're also able to see how many valve movements there's been, how many hours have we done on the pump for maintenance purposes, so we can develop a really handy maintenance program. So lots of diagnostics available in there on really anything that's moving or has some sort of power source within the system. And also importantly, we've got an alarm record. So if there's some level mismatches, something that happens to be going wrong in the system, we immediately know. And we've got those 3 levels of alarm. We've got the alarms that self-correct. We've got the alarms that stop an individual unit, perhaps a primary fractionator, but don't shut the system down. And then we've got things like a high-level bund alarm that just closes the system down. So those alarms can be then sent out to whose ever email or mobile phone as a text that you want, so that we can notify them what's going on here at site. So we've really focused a lot on remote telemetry to try and reduce the burden of operators having to be present all the time. So lots of little clever things built in to into the HMI and into the system control. That's pretty much it really, guys. There's not too much else to show you. It is really a basic concept of putting bubbles into water to fractionate out not just PFAS compounds, but actually a whole range of surface active contaminants, things like microplastics and pharmaceuticals and nonylphenols and a whole bunch of things which actually work with this process of surface active fractionation. So I'm going to be really interested over time to see what other products the system's working on. I know it's been very successful with the PFAS compounds, but what else are we able to get? What other good work can this system do? And we'll keep you posted on that as time passes. So that's it from Sweden. It's getting cold here, so we might head back to Australia and we'll see you there. Thanks for your time.
Yeah, I have to say I feel a bit cold watching that watching that video. It is a bit chilly here in Australia as well. Great to see we're getting a lot of questions through, which is fantastic. We'll come back to those at the end of the webinar with the question and answer. So But I encourage you, click on that chat box down the bottom right-hand corner of your screen and post questions there, and we'll put them to the panel at the end of the webinar and hopefully address all of those questions. Hey, Pete, back to you. Great to see. Unfortunately, you're not back in Australia. You're still in Sweden on a second trip, I hasten to add. But Pete, can you just tell us what were some of the challenges at that site, and how did you overcome those challenges?
A good jacket overcame the first challenge, which was it was so bloody cold for an Australian to be stuck in Sweden for a while. That was very interesting to be in those temperatures. But I see Rebecca tells me that that's positively balmy, so I suppose it would get worse. But that cold element was important, not just to keep me warm, but also for the system itself. Obviously, it's water; you don't want it to freeze. So we put a fair bit of work in at the front end. What do you call it? Like weatherproofing the system against these cold conditions. So we've got, I think it's 80 mil insulation on the roof and the walls to just keep the warmth inside the system. So our mandate, obviously, to the client is deliver us water unfrozen, and we'll keep it unfrozen while it's in the system and then discharge it. So we've got integrated electrical circuits that are running heaters. We run 3.3 kVA systems and nearly 10 kVA of heating potential in the system to just keep the insides warm and the system functioning. I will add that just with cold, in that separation phase, the colder the water, the better the separation tends to occur. So it's actually to our advantage in some respects. I think one of the other challenges was, the Murphy's Law would be that the first job we picked up was about as far away from the other side of the world as we could possibly get up in Sweden. So we had to have a good look at our remote telemetry and how we were going to manage that. So we did put a huge amount of effort into the control systems on board, so that from the control system back in Australia, and in fact, from any computer, from my mobile phone, I can have a look at that system right now and see how it's performing, how many litres it's done today, and I can make any adjustments I need to in terms of the sequencing or timing. So that was a really important element, was that remote control capability. And then I think the third most important consideration, if you like, on that plant was that we treated this beautiful, clean, for a couple of years we've been treating this lovely groundwater up at Oakey. It's got a bit of PFAS in it, but it doesn't have a lot of cross-contamination. And so when we hit a landfill, where you can imagine there's every possible combination of industrial and chemical ever made that makes its way down into that landfill, into this pond that we're treating, and then we're jamming it. We don't even have a pre-treatment in there now, as Elena mentioned it. We're literally putting that leachate water straight into the SAFF system. And we were worried about that water chemistry. So we chemically hardened a lot of the wetted surfaces in there, just selection of piping materials and impeller materials and valves, and just making sure that we had that aspect of complex water chemistry covered, so that for example the valve seats wouldn't swell or the impellers wouldn't dissolve. So looking at that was another important challenge. And then without boring you, there were a whole range of just little elements we wanted to make in miniaturizing the system into a 40-foot container and making sure it worked effectively. So a lot of PLC sequencing to make sure everything runs in a really effective manner.
Excellent, thanks, mate. So, Pete, we now claim that our SAFF system is probably the cheapest PFAS treatment system or technology in the world. Can we justify that, do you think?
Yeah. I mean, it's a brave thing, I suppose, to talk about being the cheapest in the world. I mean, you could stick water through a pipe and it'd probably be cheaper than the SAFF, but it's really about your dollars per gram of PFAS removed, or maybe your dollars per cubic metre of water treated might be another way to look at it if you're trying to sort of hold different technologies on a par. But if you use those two metrics, then absolutely, I think we are the most cost-effective solution on the market. And the reason for that, I guess, is reasonably easy to explain. You've got a CapEx cost, the system's costs what it costs, and of course if you're if you're a client, you've got a requirement, we'd be happy to give you a quote and you can see what that is. But we would think that it's cost effective for the treatment volume that it's putting through. And then you've got where we really surge ahead though in terms of cost effectiveness is in the operating expenditure, the OPEX, because I don't think it matters what system you're using, whether it's whether you're using any technology. I won't point them out, but whatever you might use, it really is broken up into these four elements in my mind. I think there's the labour that's involved in keeping the plant running, the consumables that you use. So are you using absorbent medias? Are you using membrane filters? What are your consumables and how much are they costing you? How much energy does the system cost to run? And how much waste are you generating? And so those four elements are relevant for any water treatment system or PFAS water treatment system. So to look at labour, as we've said a couple of times, we really focus on remote telemetry. So our target, and we're achieving it, is a 1% labour time on site. So roughly 1 8-hour shift a month to just really check the system out, kick the tyres, make sure everything's going okay. Any faults really that would occur, we would know about. I mean, anything that moves or has an electrical impulse sends us a signal, so we're able to see it anyway. But we would say you would go to site periodically. You are going to have to do things like replace impellers or I don't know, a valve or whatever it might be, but it's fairly basic maintenance tasks. So our labour costs are at around that 8 hours a month for labour. Our consumables, and this is where we really get a gain, they are zero, because all we put in is air bubbles, and air bubbles are free. And so hopefully an infinite supply of it. And energy for us, we don't have back pressure. We're really passing system through a more or less flow through system. So it's quite energy effective. We're lucky enough on Helena's system, we decided to really drill into energy. And I think I mentioned it on the video. We really wanted to see how we went with that. So we categorically know now, after having treated, many millions of litres over here, or gallons, that we're using between 0.6 and 0.7 kilowatt hours per cubic metre treated. So I don't know what power's worth in your neck of the woods, but for us it's 10 or 12 cents for commercial power. So we're looking at 6 or 8 cents, whatever it is, 7 or 9 cents Australian to treat a cubic metre of water. So I think that's very effective. And then waste, as we've said, like at Oakey, we actually haven't paid anything for waste because people were good enough to take it away for us. But even at the sort of landfill sites, which I think is the other end of the spectrum, where you might be generating a reasonable volume of waste, the reality is in a given year, you would be very lucky to put 2 or 3 IBCs of waste out of these systems. And again, I don't know what a cubic metre of waste costs in your part of the world to get rid of, but in the scope of the whole system, it's probably a fairly minimal cost. So because of those reasons, we actually think that the SAFF is literally orders of magnitude 10 to 100 times cheaper to treat a cubic metre of water with air than it is with any other media. So we're happy to be proven wrong, but that's our belief.
No, it's good. It's good. Got plenty of questions still coming, which is good. Helena, I'm going to just go back to you, because we've talked a lot about the co-contaminants that we're dealing with at Talia, and normally that would require a really robust pre-treatment plant. You showed us some of the stuff that you'd put in place there, but my understanding is what is the pre-treatment for the SAFF 40 at the moment?
Well, the pre-treatment, as we started this project, that came in kind of early after I came back from Australia. And, I didn't know much about the pre-treatment system, but we were going to use one for the GAC. So we kept that on in the beginning. We kept it on as a precaution, as we haven't seen the SAFF working before. But as we was trialing it, it was just chugging along really, and so we bit by bit took it away. So in the end, now we don't have any pre-treatment systems at all. So we are just pumping leachate straight into the SAFF and then straight out of the SAFF. This was a fairly good starting project, the only criteria for the project is PFAS, and that's 50 nanograms per litre. And in the beginning of the project, I just asked Pete if he will feel confident going into such a project, because it is a really hard water to treat. But the PFAS, the SAFF has shown really good potential for doing that. So we took a leap of faith and going into it, and it has proven to be a success.
So the only pre-treatment we go is through the filters, is that right? The filter bags at the start of that project.
There's 2 onboard bag filters.
That's it. So yeah, it's pretty amazing. So Helena, what I want to do now is just I understand you and your team have been doing some laboratory tests there using the bench scale apparatus that we sent across to you. I'm just wondering if we got a picture of that we can put up, that little bench scale unit. So my understanding is we were going looking at sort of predictability modeling through us, and then you guys were lab testing and then field testing. Can you talk us through some of the results that you've had in that process?
Yeah. Well, as I came home from Australia, I really wanted to get this method going. And so I asked Pete how we were going to do that. And he was kind enough to build me this bench scale model that you just saw in that picture. I was trying to get clients to try it out, and we got a fair few interest, both from universities and clients and organisations. So from that on, we have trialled quite a few waters. I think it's about 20 now, ranging from anything from groundwater to processed water and wastewater. And so, yeah, and I think we were going to, if we can bring out that slide we had before. No, if we go back one, yeah, thank you. Yeah, because when I was given that bench scale model, I was also given this prediction model, and that is something that you guys have taken, just made up from the data that you have received at the Oakey plant over the 2 years. And so Pete said, well, this is what we're getting for groundwater, but we have also seen it for other waters that we've trialled. So see how you go with that in your bench top scales that we did. And so this is the removal percentage that we were hoping to get. And so we started, and already the first trial was really interesting. It was the IVL, the Swedish Environmental Institute, who was doing a report for the industry. And we got to trial together with the IVL about 5 leachates from all over Sweden, very different ones also. And this is a slide that I stole from IVL as they did their presentation, and redid it just a little bit just to be more clear. And it shows in the first column there, you can see the PFAS compounds, and in the second one you have the carbon chain length. Third one, you have the OPEC prediction model for groundwater, the one you gave me from the Oakey site. And then in the fourth, you can see that the test results that we've got with the mini bench scale for these waters, for these lead-shaped waters. And as you can see, we were just, really excited because the results were lining up really well. We are removing 100% of the C6 chemistry and above, almost all of them. And we're also removing quite a few of the short change ones. So that was really exciting to see that the groundwater prediction model actually worked just as well for the leachates. And just another thing that the IVL threw in this table here is the half-life of PFAS in the human body. And as you can see, all the long chain ones that stay in the body for quite a few number of years, we'll take away almost 100%. So that was a really fun trial that got us some really exciting results. But I just, I was getting quite a few interesting clients. And so this is a client that we trialed for. They had about 8 waters ranging, as I said, anything from groundwater to wastewater. And I picked some of the waters out here because I think they really show the potential of the treatment method. You have here also, you see the carbon chain length and the ingoing concentrations. And then we have a treatment time of 10 minutes here. This first water has low in suspended particles, really high DOC, you can see it's in the 1200s, and a low pH of 3.8. It also had a low PFAS level, but we didn't know that at the time. But when we saw it, we got really excited about that too, because even though we had 107 nanograms per litre going in, we were still doing 97% removal. And looking at the data, the predictive model versus the results that we were getting, where we have levels, it sort of matches quite good also for this water, from the prediction model versus the real results. So it was exciting. But we didn't stop there, of course. This is a runoff water from the process industry of this site. This one's a bit different, normal DOC, and and also like a lot of secret ingredients. You could actually see like some conglomerates of weird stuff that we don't know about walking around in it. So we were wondering how this was going to go. We had a PFAS level of 7,700, and coming out of that removal process from 15 minutes, we also did a 28-minute trial. You can see that we're up to 83% removal for some of PFAS 11, which is the Swedish 11 as we call them. And once again, you can see the prediction model lining up really nicely with the results. The last one, I can't get enough of results, so I just got to chuck them all in. I can't choose. This is for a groundwater. So this is a really clear groundwater, so lower level of DOC and TOCs, but a really high level of PFAS compared to the other samples. You can see here as well, the prediction model lines up with the SAFF, and we get a 91% removal. So that was really, really exciting. And then at the end, it was time for, then we had won the Tell You project where we are showing the plant. And so this was a nerve-wracking trial because this was actually the one that we were going to do full scale. And so we had some lower levels going in this sample, so around 850 for PFAS 11. But we did really well from the removal rates on this water as well, despite the algae and everything else in it. And especially for PFAS, since we had a target level of 50 nanograms per litre, and that was our only target. So I was really relieved when I saw these results. And concluding from these 20 tests that we've done is that, I was given a prediction model for groundwater, but actually I just crossed the groundwater out, and it's now a predictive model that I use for all waters that I do for clients to see how we can treat their water. And these are the, once again, the removal percentages that we are sort of getting. Oh, and we're getting to the full-scale results where they are super interesting. So I almost forgot about them. So in the first column, you just see the PFAS compounds. In the second one, you have the removal rate from the prediction model. The third one is the results that we were getting with the bench scale mini SAFF and a 15-minute treatment methods. And then to the far right, you can see the removal rate that we have had for after 15,000 cubic meters. I think that's about 4 million gallons, if I'm right. And then we do a 19-minute treatment cycle for this one. And as you can see, it lines up pretty well with the removal rates. And we are getting sort of mostly better results than the mini SAFF. So it's been really good. Really excited about that. Oh, this slide, I'm such a concentration girl. But this is just showing you concentrations. So if you want to look at this, later on when you come back to this webinar, you can dive into the numbers to get a bit more data.
So that predictability model, you did another sort of full field test as well using that SAFF 40 that we had on site. Can you talk us through that, Helena?
Yeah, that was just as unexpected as it was interesting. So when we were starting up the SAFF, we had quite a few clients coming around, of course, to show it and show the results that we were getting. And one of them were the Swedavia airport people so they are in charge of the Arlanda airport, which is the biggest one in Sweden. And I had promised them a trial further on, but as the second SAFF system was also delayed due to COVID, they just said, well, why do we need to wait for this second plant? Can we just drive our water here and you can try it out? You have such a nice full-scale plant. And I said, well, yeah, we could ask the client, and that was okay. So it just took a couple of days, and then suddenly they showed up with 40 cubic meters of PFAS contaminated water. And so we cleared out our 38 cubic meter sediment container and topped it up there. And within a couple of hours, we had just run these 40 cubic meters throughout the system, and just trialed it for, incoming as well as outgoing. And I think, here's the results. We used the same sort of 20-minute treatment cycle that we were doing for the normal leachate. And these are the results that came in. So we have an untreated incoming concentration of about 1,500 nanograms per litre, and we are removing, without any pre-treatment or anything, we have a removal rate of about 80% just with the SAFF. And to the right, you can see the OPEC model, just comparing it. And you've got to watch out for the low numbers, because if there's no concentration, it's really hard to remove it. But otherwise, once again, it just lined up, and this is full scale. So another really super interesting results.
It's good to see that all of those things lining up. Pete, I know you wanted to talk briefly about this slide, so just give us your thoughts on this.
Yeah, thanks, mate. I just put this one together reasonably recently to just throw into the slideshow, because it's kind of this key message, I guess, was that when we started with that predictability model, we weren't sure if it was going to work on anything other than groundwater. But now we've treated a whole bunch of different types of water, so you can see them on the left there. So we've got groundwaters heavily contaminated in the tens of thousands of parts per trillion. We've got lightly contaminated waters in the tens and maybe hundreds of parts per trillion. We've got landfill leachates that we've done. We've got hydrant waters that we've tested, RO rejects, the brine from RO, which obviously contains a lot of PFAS. Various industrial process waters, construction, drinking, treated sewage. So we've done those, applied the predictability model for them for various clients. We've done lab scale bench testing across all of those. And bear in mind, we're not just doing bench testing here in Sweden. Helena's done about 20, but we've also been working with the CDM Smith guys at their Bellevue lab and done a bunch of sampling over there with Zoom and the team. And back here in Australia, we've also got the teams at Macquarie University and the University of New South Wales, who have been doing more testing for us. And then internally in OPEC, we're also doing testing. So we've got this really great broad range of water types. And now we've done the predictability model, we've applied, we've got it at the lab scale, and now we're moving into this full scale, which we've done for groundwater and leachates, and we're moving into some of these other trials at the moment on the full scale. Dave did one the other day on a sort of industrial water that we used. We spiked up on a new high performance SAFF system. So we're really starting to prove or give a level of confidence to clients that if it works in the predictability model and the bench scale, it's going to work as well or better at the full scale.
Yeah, it's exciting just to see those results and see how everything lines up. Hey, Dave, I'm going to come back to you if I can. Yep. What are some of the common misconceptions regarding foaming leachate to remove PFAS?
I guess there's two main issues. So the first issue might be that some water treatment engineers or integrators might get worried about waters that excessively foam and potentially flood the aeration column. The second one could be that the engineers are also worried about creating a large waste volume of dilute PFAS, and then they have like their original feed water plus the waste that still contains the PFAS still to treat. But they're valid concerns. And typically that could happen if you're trying to run a foam fractionation process as a single stage foam fractionation, small diameter column. That's not going to work. So the process that works for OPEC Systems is that we've developed our multi-stage foam fractionation process, as I mentioned in the beginning, that the first primary stage strips to meet the criteria, and the second stage of secondary and tertiary enriches or dewaters the waste into a small volume. So that's basically what we do. And then during our laboratory feasibility studies, we determine if a feed water is going to be one of these more difficult projects that does excessively foam. And all we do is we manage the parameters. And over at the Tellier site, we just detuned or turned down the gas velocity or the aeration, and tweaked a few other parameters that I won't mention here. And we managed the process to make the job work. And that's what you do.
Yep. So it's good you say that, because yesterday you and I were out. We've got another SAFF 40 which is just about to leave here and go across to Europe, which I hasten to add, all of those SAFF 40s we're developing now. We've got EU certification for the European ones, and the US one that's currently under construction is going through the similar certification for the US market. But when we looked at that SAFF 40 at Penrith yesterday, what are some of the differences between that unit and the unit that's currently at the Tellier recycling facility?
Yep. The designs are essentially the same from a design treatment logic point of view. Obviously, with the Tellier site being one of these projects that presents feed water that's got a lot of algae in it, excessively foams, we needed to do a couple of on-the-job, on-the-fly workarounds to manage that excessive foaming. So these have now been fully re-engineered into the design of the plant that we had at the open day yesterday. The main one being that when the primary foamate comes out of the top of the primary fractionators and fills tank 3, which is an ullage transfer tank, once that volume is exceeded, if we are receiving excessively foaming concentrate, we can manually divert that through an overflow pipe to an external, very large tank. It might be 5,000 litres or 1,000 gallons or something or larger, and then it gives it time for the foam to collapse back into a liquid, and then we put it back into the plant to continue the processing. A couple of other workarounds and re-engineering that we've done is that we've relocated there's a little GAC system in there to trap any aerosol or vapor that may contain PFAS or volatile PFASs. So that now, as you can see on this image, they've been replumbed to be external to the container to provide a bit more space for the guys to do maintenance and warranties inside the container. So none of the air is vented to the atmosphere without going through a GAC cartridge that you can see there in the red circle. And in the future, we might even need to stick another cartridge in line on top of that to take out different types of volatile PFASs as they come under more scrutiny. But at the moment, they just go through a twin GAC cartridge system before being expelled to the environment. And then the last couple of things that we've done is we've put in a few more washing access ports to be able to clean out the system if heavy foams do go through it.
Yep.
And Pete and the guys have been reprogramming the PLCs and the HDMI to allow for automated scheduled cleaning in the system. That's probably the main ones.
Yeah, I like that. That was a very elegant little solution to take quite a big drum that was inside the unit and actually move it outside into two smaller drums. Hey, we're getting close to the end of the webinar. There's just two questions I want to address which look at the future. And so, Dave, probably the first one is still with you. Can you tell us about some of the ongoing studies and research we're currently involved in at the moment?
Yeah, the one that is most exciting for me is a collaboration that we're making with CDM Smith in the US. They put a proposal to the ESTCP group for a downhole foam fractionation installation as a trench, which is approximately 10 to 12 metres long, 1 metre wide, and might go down 5 to 6 metres deep. That trench is filled with a gabion cage, wrapped in geofab, backfilled with an aggregate to allow the aeration pipe to go through the base of the trench, allow the aeration to rise. You can see in that image that the primary fractionation vacuum hoods are at the surface to remove the stripped PFAS, and then we take that back to either a SAFF 20 or a SAFF 40 to dewater into the final reduced waste volume. So that's really exciting. That one's going to start in the fall of this year in the US. The next one, we're continuing to do our work with the University of New South Wales as the lead and Macquarie Uni as support for another both in situ and ex situ fluid fractionation of foam fractionation separately and in combination. Another one that we're doing internally on our own, we've been intensifying and optimizing foam fractionation as a single primary fractionation vessel to, I guess, chase the trade waste market. So this is small to medium industrial clients that potentially have PFAS in their wastewater streams and it's being disposed to sewer. We've got a system that can aerate for like 20 odd minutes, remove the PFAS and then dump the water straight to sewer. That one also allows us to chase that other market where we're able to remove PFAS from the ultra trace feed water streams. And then finally, with the great results that we've been getting out of Oakey for the past 2.5 years, Pete and I, with Paul Stevenson in the UK, who's a foam fractionation expert, we've penned a manuscript together and we've submitted it to a journal to get it published, peer review published paper. I won't mention who the journal is yet because it hasn't been finalised that it's been accepted, but we hope it will be and they'll get published in the near future.
I can't wait till I'm next at the airport and I'm going past and it's in the bestsellers rack. Hey, yeah, pretty exciting with that industrial trade waste. Some of the results we've seen of the initial testing has been phenomenal. Pete, we are really starting to come close to our time limit, but very quickly, can you tell us just some of the innovations that we're looking at for being able to deal with SAFF production going into the future?
Yeah, no troubles. I'll keep it quick. So really for the last year, as we've sort of seen this demand starting to emerge, we went back to the drawing board on two fronts. And the first was the design. So the SAFs that you've seen through the presentation, I guess they're bespoke built. We fit out the containers as we go. We've moved to a modular design. So every primary fractionator, every secondary fractionator, every bank of tanks are all in a module, and those modules will all be about 7 feet wide. So you'll have 5 to 6 of them in a 40-foot container. I think it's 5 of them, and so we've modularised that so we can start to pre-manufacture elements that will just slide into side opening containers. And the intent of that was to try and reduce the production time from order to dispatch down to 2 weeks. So from time of getting an order to the time of putting it on the truck to ship off to the client, we think we can do that in a 2-week period. We're also building an agile manufacturing plant out in Western Sydney with the intention of producing 1 system per week out of that plant. So we realised pretty quickly when we started looking at the size of the market that if we kept hand building these systems, we were going to quickly fall on our own sword by not being able to meet up with demand. And even now, we've got a flow of orders right through to the end of the year. But by the end of the year, that agile manufacturing plant will be in place, and so we'll be progressively ramping that up to be able to meet demand. And I think it's important for the market to know that.
Yeah, I mean, it's exciting for me because I love that way we're looking at the systems and trying to really streamline that. Look at how we deal with long lead time items and getting those consultants in to give us advice on that. Certainly it won't happen overnight, but I think our plan is to get that to those target figures that you said within sort of 12 to 18 months. So it'll be challenging, but I think as OPEC always does, we rise to the challenge. So that'll be good. That brings us to the end of the sort of structured part of the webinar today. I hope you've enjoyed it. For those people that are watching, if you need to peel away, then we thank you for joining us. We are going to go into the question and answer session now, but if you need to peel away now, that's fine. We'll send you a link which will include the answers to the questions that have come, and we've got actually quite a lot of questions here, so we could be here for a little while. In the meantime, if you've got questions from the webinar that you don't think we've adequately addressed, please send those questions to either of the three panelists here. Their emails are up on the screen now. Again, we heard a lot about the predictability model, and so I'd encourage you, if you've got lab tests from the water on your site, you can send them through to Dave in the first instance. We can run them through our predictability model. That's free of charge. And then if you want to then go to the next step of putting it through one of the bench top laboratories that we've got one of those in Europe, we've got one of those in the States, and we've got one in Australia. We can actually do that testing for you with the ultimate aim of giving you assurance that if you go to a SAFF 40, SAFF 20 system, it's actually going to work for you. And I think so far we've demonstrated that predictability model is working. Please follow us on LinkedIn. There will be some more webinars. We gave you some tasters for some of the webinars that are likely to come out in the next 6 months. There's certainly a lot of activity and a lot of research and development that we're continuing to do here. So I'm just going to go now to questions. If you've still got questions, you can still log them in that chat box, but I'll go to some of the questions we've got here. So Jim has asked, and Pete, I think it's for you, what is the pre-treatment in the PID? So
to be honest, I'm not sure what PID means, but I assume it's in the plant that was on site there. So the pre-treatment was originally flocculent, clarifier, lamella settling tank, but as Helena had mentioned later in the presentation, we've actually removed all of that. That tent is now all but empty. We've got a little settling tank in there just to dump the water out of the lake. It doesn't do any treatment, and then it runs from there into the plant. So literally the only pre-treatment we've got is two the now 25 micron bag filters, which I only changed out the other day. So they're lasting about a month. They're picking up the fine colloidal phase, and they're picking up an element of the Helena's dreaded ghost, the algae. The SAFF doesn't really mind a bit of a load on it, so there's not a need to kind of pre-treat it to within an inch of its life. It's just not that fussy.
All right, and Emma has asked, what or where is the site in the States?
Look, I can't unfortunately tell you because we're under NDAs, but it's on the East Coast. It's going to move across 4 different large sites over the course of the first 12 months. And so there'll be plenty of good data coming your way on the US sites. And as soon as we get permission, we'll release that information.
Excellent. Phil has asked, what is the float or settled material that was removed before the clarifier or GAC?
Yeah, well, as we said, all that algae and that's we needed to take that out, and we use this special flocculant. So that's just flocculant and stripping out, and then that just falls to the bottom of the lamella and gets taken away from there. So not floated, but settled. Yeah,
I mean, most of that is actually suspended solids, I suppose, including the algae phase. So it's just quite a cloudy water. We're not dredging from the bottom. We don't have a lot of floating mass. It's actually just the suspended solids. It's relatively turbulent. There's water coming in there all the time. It's fairly shallow, so it's also sort of wind agitated. So it's just dealing with that suspended solid load.
Yeah.
All right. Rebecca obviously loves the way we've modified it to deal with the balmy temperatures you've been in. Phil has asked, we're having trouble removing PFHPA. What is your experience with this compound? Well, Phil, my experience is nothing, but these guys.
Well, Dave, do you want to have a crack at that, or do you want me to?
Yep, so that one, like I think if we go to slide 12, I think that might be on this slide, and it'll show that we have partial removal. Let's see if we can get. Get that one up.
PFAS in 2 samples varies from sort of high 80s or 90s to the high 60s. We don't get it all. And a lot of this is the interesting work that Paul and Dave and I have been doing around this concept of the Langmuir constant. So the ability of surface active foam fractionation to work is very dependent on the solubility or otherwise of the PFAS compound. So when you get around that, there's this kind of really critical, interesting point around 1 × 10⁻⁶ meters. When your Langmuir constant is lower than that, then you don't tend to pick up those compounds. And PFHPA from memory is about 0.9, so it just sits under that critical point. So then we have to trick the absorption isotherm. We're trying to drive down it by varying things like the conductivity and lowering the water temperature and just trying to make the conditions more amenable on the isotherm so that we can get it. But it sits in that kind of right on the cusp, and we can often get it, but sometimes it's not as effective as others, whereas things like PFOA and PFHXS and some of the other ones, we're super confident. We never seem to miss those ones because their Langmuir constant is well above the one.
Yeah, the whole concept that Pete's talking about there is all about the adsorption coefficients for a PFAS molecule to adhere to the air-water interface of a rising air bubble. And it's that's one of those compounds, the C6 to C5 carboxylic acids are in that funny zone where they sort of do and they sort of don't. Once you get to the C4 carboxylic acids, we find it really difficult to get them to jump onto that air-water interface.
All right, well, Phil, hopefully that's answered your question. Rebecca has a specific question for Dave.
Great.
You guys can stand down. Dave, have you completed any capture measurement of the air volume in the concentrators? And does the phase of the process require any venting air emissions? I ask because of the potential for a few certain PFAS constituents to volatilize with the right Henry's law constant and molecular weight.
Molecular weight, yep. So we have characterized the air flows and gas velocities, but we probably don't really want to disclose that here in this place. We can probably have an offline discussion about that. It's a bit proprietary for how the system works. But obviously, we are aware that when you introduce aeration into contaminated feed water, there's 2 mechanisms that might occur here. The first is that the adsorption coefficients allow certain PFAS to attach to the air-water interface of rising bubbles. Obviously, that's how we get the PFAS out, or specific legacy PFAS out. But the other group of co-contaminants that are potentially also going to take advantage of rising air bubbles are ones that have a high Henry's constant. And these could be chemicals like trichloroethylene or benzene. Them not so much going to jump onto the air-water interface, but they're going to form an equilibrium between the dissolve phase and the gas phase inside the air bubble. And obviously there's potential for the air bubbles to take up these volatile compounds. Some of them might be volatile PFAS as well. We're not really sure how they would either attach to the air-water interface or move into the gas phase inside the air bubble. But obviously this is the reason why we vent all of our exhausts through that GAC twin manifold on the outside of the container. And in the future, the system that we're going with allows us to add different types of media on top of that exhaust to capture any of those.
I think we've covered your question there, Rebecca, I hope. Phil has asked, does the leachate foul the media after the foam fractionation? And then he's got iron biological fouling.
Well, the short answer is there is no media after the foam fractionation on the leachate plant. I mean, whether that media was GAC or resin, we find that they're not a very good fit. I don't want to speak for Helena.
Yeah, no, we did that GAC trial and, it took 4 days, even though we had this really robust treatment system. we really gave it a go, I think. And so at this site, I think polishing will be really hard. It will be economically unviable. Yeah, we're reaching the target criteria of 50 nanograms per litre without it. And I think that's the rescue for that site.
Yeah, I mean, it's probably worth saying, if you didn't get a chance to look at those results, like our target's 50 nanograms, but consistently over 10 or so weeks now, we've been below 1 nanogram for PFOS, other than I think 1 week we were at 1.4 nanograms. So it's not jammed, but it's also doing the same for PFOA and PFHXS. Like, it's stripping a lot of that PFAS chemistry out of there. And I would say it's in the high 80 or 90% in terms of bulk detectable PFAS that we're testing for is getting removed. So very little is actually getting discharged to sewer. I mean, it's a huge lowering of the PFAS burden for the downstream sewer treatment plant when we can remove that high percentage, particularly
I think
all of the long chains.
I think Phil's making the same point. Does the costings that we put up include the GAC for polishing? Well, we don't have GAC in there for polishing in that particular site.
I mean, that's the strength of it, Phil, is there's no absorbent media, and that's a conscious thing. You know, we're just trying to see how far we can take air bubbles, and so far, if you can remove them all with air, why really would you bother with an absorbent medium or a resin? I mean, they're consumable, they generate waste. If you can get away without them, then you don't need them. But there are circumstances, of course, where in regulatory environments, as they become more stringent, you're going to chase those short chains. I mean, PFBA is like the problem child of PFAS chemistry. It's very hard for anything to get. It's the first to break through any absorbent medias. We only pick up perhaps 20% of it at best. So those kind of products, as regulators set those as a target criteria compound, I think it's one of those cases of be careful what you ask for, because they're really hard to get, and they could cost a small fortune to chase those. And then that's why I think Andre's table about how long PFAS reside in blood, for me, is quite compelling. You know, some of those short chains, I mean, they're in and out of your system in a matter of minutes. So, of course, if you've got continuous exposure, that doesn't mean that they're not going to cause harm, but there really is a lot of interesting philosophy about how much of these compounds you chase.
So, Barman has asked, what is the typical energy consumption of a 3-phase foam fractionation system?
So it is 0.6 to 0.7 kilowatt hours per 1,000 litres or per cubic metre or per 250 gallons that you put through it. So in a day at Helena's plant, we're doing 350, say 400 cubic metres per day. So we're using about 300 kilowatt hours of power to run that plant. So in terms of power costs, it's probably about $30 a day, something like that.
Okay. Jim has asked, what are the options for destroying the super concentrate?
Yeah, I actually forgot to mention this when we were sharing the screen for that downhole foam fractionation trench design with CDM Smith. So on that installation, obviously the tertiary foamate that we remove through the SAFF 20 or the SAFF 40, that would be handled and destroyed by CDM Smith's own in-house eco electrochemical oxidation cell. But yeah, OPEC Systems is kind of agnostic when it comes to these destruction cells. So the lane we swim in is we want to be able to focus on being the best company out there to do separation and concentration of PFAS from water, regardless of whether anyone in front of us is doing soil washing and we treat the soil wash water, whether it's various types of waters. The concentrate, we then can give that to others that we team with. So that might be folks that have a supercritical water oxidization cell, an electrochemical oxidation cell like CDM Smith. ACOM have got one as well. The folks at Ramboll, I think they're developing a a reductive defluorination cell. There's other people here in Australia that have got a mini plasma arc. Clocks in uni have got like a similar cold plasma system. There's a whole heap of them.
Incineration, which
so if you want to go the really old-fashioned route, just put it on a truck once every 5 years and take it to an incinerator.
Yep.
But yeah, we've purposely stayed out of destruction so we can just concentrate on separation and concentration and be able to team with anybody and I guess not step on toes.
Yep. So Jim's also asked, does OPEC train client operators?
Well, the short answer is no, Jim, because we haven't actually got a system in the US yet. So the first system will arrive in July, August, and of course, we're working. If I use Helena's company as an example, then Johan and Bjorn, the two guys who are on site, absolutely. We've done formal and informal training on the use of the system, the maintenance of the system, and the operation of the system. So if you've got a SAFF plan on site, we're certainly not going to leave you hanging. We'll work with your people, whether they're your own people or your contractors, to make sure they can run the system effectively.
Yeah, we were certainly exploring a number of different models of bringing people into Australia to train them up as being a certified SAFF operator or training on site. I guess COVID has certainly thrown some of those plans around a little bit, and we've had to do a bit of tap dancing, I guess, is the short of it there. So, Scott has asked, hi, David, any updates on establishing bench scale testing capabilities in the US?
We actually have one. We've had one in the US maybe for 2 years, I think it is, Pete.
No, it's better than so,
yeah. So we actually built two $25,000 1 to 50 scale models of the Oakey plant, a semi-automated system. So it's primary, secondary, and tertiary. One obviously was sent to Helena, and she's been showing that around Europe with various researchers. The other one we sent over to CDM Smith's Seattle lab, and they've been using it on a number of their client projects. And we are open to, I guess, CDM Smith's competitors to consider sending site water to their lab if they're willing to do that. There has been the odd occasion where some of their competitors chose not to do that and actually sent a few hundred litres of water from the US to our Australian lab here in Sydney. That's part of Macquarie Uni, where we've done the same work on the same gear. But yeah, at the moment, probably for this year, we wouldn't establish any more of those benchtop apparatuses anywhere else, but for the ones that we already have. It might change in the future, but not in the foreseeable future.
Sure. Stephanie has asked, in the treatment cases presented, did the water foam naturally? Does this depend on co-contamination?
Well, we trialed, those 20 waters, quite a few didn't foam. And so we did different tests. In some of them, we added just a little bit of dishwashing liquid just to see how that goes. And but in others, we did both dishwashing liquid and not. And we have seen that we managed to get the PFAS out anyway.
Yeah, and, so the PFAS comes out in one of two ways. So the obvious one, the visual one, is the foam. It sort of spills over. The other element is you do get stratification in the water column with an accumulation of PFAS in the very upper layer. And so we do a top-up overflow process at the end where the top layer of water is spilt over the weir as well. And we capture a lot of PFAS in that non-foaming environment. But there's a couple of possibilities. One is that if you've got a very low foaming situation and you want to enhance it, it is possible to add biological surfactants that will support the foaming process. And in that foam architecture or matrix that you create, the PFAS come out with that. And then the other thing that Dave and I have been working on is to actually, once you kickstart it with the surfactant, and you're starting to remove and create PFAS concentrate, is having a bleed line back that feeds a small portion of that PFAS concentrate back to the primaries, so that we can actually induce foaming using that concentrate that came from the source. So we're not actually adding any amendments. Again, these principles of green chemistry and sustainable engineering, we're trying to move away from any additives. So if we can recover the PFAS as a concentrate and then use that to stimulate foaming in the low foaming waters, and then recover that in the later fractionation stages, we think that that's a beautiful outcome, really elegant.
Yeah. And the other thing that I might add is that in our new high performance foam fractionation vessel, we're able to make potable water and even reverse osmosis treated water out of the lab froth.
Yeah.
So we might not even need to do that.
Well, I do remember from our third webinar, that was one of the beauties of the SAFF system when we were talking about CDM Smith's destruction thing, is that there were no co-contaminant or nothing added to that that treatment, so that it made their destruction technology work far more effectively.
Yeah. And the other thing that works for foam fractionation primary or stripping is that the more monovalent electrolytes you have in the water, so it could be from hard water, minerals in the geology, the better it works. Because you have to remember that foam fractionation's first big commercial use was in marine aquariums, for the aquarium hobbyist market.
Yeah, you don't want to be adding stuff into your local aquarium. Hey guys, we've just got a couple more questions from Yasser, and Yasser, I hope you're still on watching, because you've hung around to answer these. But these are great questions. So, is it a batch treatment or an enlightened treatment plant? And I think we went through that in your video there, Pete.
Yeah, look, we've coined the term semi-continuous batch, and it's one of those suitably ambiguous terms that we put in. I mean, it's not continuous. It doesn't flow from one primary to the next, with the concentrations getting lower from primary to primary. Each primary gets a fresh batch of contaminated water, and it treats it over a cycle, whatever cycle length you need for that particular water chemistry, and then it discharges it. It doesn't feed it to the next primary. So in that respect, it's batch. But it's continuous or semi-continuous in the thing that, as with multiple primary vessels, one's filling, two are processing, one's emptying, and so the actual input of water and the outflow of water is more or less continuous. So in that respect, it's a semi-continuous batch.
Yeah, and I guess if you read Paul Stevenson's monograph on foam fractionation engineering principles, it's semi-batch, meaning that the feed water pumping in and then pumping out is batch, but the application of air via aeration is continuous. That's why we call it semi-continuous. It's multi-stage, because there's primary, secondary, and tertiary, aligning stripping with enrichment, and it's continuous in the fact that we always have water coming out the output end to be discharged, or potentially like what we do up at Oakey, it goes through a GAC, guard column, to remove DOC, followed by a twin lead lag long chain resin system that we get from Lanxess, and then it goes into another lead lag Lanxess short chain resin setup.
All right, just one final question, I think, unless we get any more in, but are there any limitations to your system, whether it's the concentration of PFAS in the water or the types of contaminants in the treated water?
That's a brilliant question, Yasser. And so,
shame I didn't ask that one right at the start. But,
I really like that question, because it actually brings up a really important element of the technology, which is, unlike a lot of other tech which use absorbent medias, the beauty of SAFF is it literally does not care if the influent concentration is 10 parts per trillion or 10,000 or 100,000 parts per trillion. The cost doesn't go up. You're not using any more. There's no consumables. So you're not using anything more. It's just that the air bubbles become more saturated the more compounds they get. And so you might generate more foam if you've got higher concentrations, but there's no limits. The only limit might be a lower limit. So we've seen in the single-digit part per trillion, 3, 4, 5, where we're getting removal down below the limits of reporting, which we're typically using 1 nanogram per litre or part per trillion. So the lower limits are in the single-digit parts per trillion. The upper limits are in the hundreds of thousands of parts per trillion. In terms of cross-contaminants, the only thing I'd say that might harm the process is if you had heavy free oil. And so we would have some sort of a coalescing plate separator if we were likely to encounter, say, a plume of avgas adjacent to a firefighting training area, which might be a common scenario. So we'd probably put in a coalescing plate separator, which might get it under 30 ppm, which is that kind of visible sheen range, and then it wouldn't make a difference. And the other thing is anti-foaming agents. Like, we like foam, so if you had a really heavy amount of anti-foaming agent in the mix, that might negatively or adversely impact the process. But so far in all the waters we process, the cross-contaminants don't matter whether the DOC is up or down, salinity is up or down, metals are up or down. It just keeps kind of plugging along. Because again, you just think of the basic physics of what's happening here, like the physical element of what's happening. It's a water tank, you're putting bubbles in it, you've got surface active compounds in there that are adhering to air bubbles and rising up and taking a ride to the surface. And so if they're not surface active, they don't interact with the air bubbles, they just kind of move their way around them. If they are surface active, they accumulate in this beautiful rich foam, which we then take and concentrate. So it's very versatile in that respect.
The other thing to mention there too is that SAFF can be positioned anywhere along the treatment, migration plume on a site, but to work on low level all the way up to source level concentrations. But where you get the most value for your investment dollar is if you feed water that's contaminated with PFAS from the source zone, because it basically costs you the same CapEx and OpEx to treat source water that it's going to cost you to treat boundary water that's at trace level. But if you treat it at the source, you're stopping it from going to the boundary and become a problem to your neighbours. So if you can do that, that's the best place to whack it. That's also the best competitive place where it outcompetes GAC and resin, because the higher concentrations that GAC and resin have to deal with, that's going to cost you more money. Yeah. SAFF doesn't have that problem.
Yeah. All right. Well, guys, we have concluded the questions. Once again, if anyone is still online, thank you so much for hanging around and asking those questions. And you guys, my panelists, thank you for answering those questions. Guys, we'll let you head off. I suspect it's evening there in Sweden. We're about to start our day. Thank you so much for joining us. Have a great evening. And for those in the States, look forward to watching the pink moon tonight. We've already seen it here in Australia, and it was fantastic. So enjoy that little light show tonight if you can see it.
Thanks, Connor. Thanks, Dave. And thank you, everyone else. We'll see you all soon.
Yeah, bye, everybody.
Bye.